All right, for calculus, this is 1.4, and for pre-cal, this is us going into calculus, but according to our textbook, it is 1.3. And this is on continuity. So we started talking a lot about continuity 2 sections ago. We talked about how we can see holes, jumps, and asymptotes in a graph, and that would break up a graph, making it discontinuous at a certain point. And we saw what those graphs look like. So now we're just going to go more in depth, especially with talking about limits. So the formal definition of continuity is that a function f is continuous at a point C if all three of these statements are true. The first one says f of c is defined. And all that means is that the point at c exists, okay? The second one is that the limit as x approaches c for the function exists. And again, that just means that the limit exists. And the third one is that the limit as x approaches c of the function is equivalent to f of c. All that means is that when these two exist, they have to exist at the same exact location. So let's check out some visuals for that. So this first image is the only one that is continuous, okay? So if we look at our drawing, the limit from the right and the limit from the left are approaching the same location. So the limit exists. And you can see that the point also exists at that same location that the limit exists. Therefore, it is continuous. Okay? Visually, it seems like, duh, of course it's continuous. I don't have to lift my pencil to draw this, which is another good rule of thumb to use. But we're going to start asking for more formal definitions. So let's look at the next one. If I look at the function from the right and from the left, it's going to the same location. So the limit exists. And the point exists down here, but the limit and the point are not in the same exact location. Therefore, it is not continuous. For this next one, from the right and from the left, going to the same place. Therefore, the limit exists. But the point, f of c, is not defined, meaning it does not exist anywhere there. Okay, I can't fill in that hole. Therefore, it is not continuous. And then for this next one, we have... Sorry, I made a little mistake here. I had to change my word here. We have that from the right and from the left, the function is going to two different places. Therefore, the limit does not exist. And technically, you can stop there because you already did not meet one of these three. But just to keep going, you can see that the point exists up here, but the limit doesn't, and they would have to be in the same spot. So therefore, this one is not continuous either. Okay? Now, when I start asking you questions about the intervals of continuity, there are about 3 different ways that we can say this. Let's look at these images. Okay? So first, I can tell you that it is continuous on an open interval from A to B, and A and B would be numbers, like let's say from 2 to 7, and open intervals are placed with parentheses, okay? Whenever you see the parentheses, it means open interval, and that means that you're including every number in between A and B, but not including A and B. An example for that one is this first image, okay? On the graph, you'll see open circles for open intervals, which are parentheses. So that means everything in between A and B exists, but A and B is not counted as part of the function. Second scenario is continuous on a closed interval from A to B, and that's denoted with brackets. Okay, and that means, that's the second image here, that means you're going to include everything from A to B, including A and B. So you can see it looks a lot like the first one, except A and B are bubbled in, means that we're including them. Okay? And then the last scenario is a combination of two where I can include one end and not the other. So again, one of them having a bracket, one having a parentheses. It could be like if on this one I just filled in this one side, or vice versa. Another example is infinities. Infinities get the parentheses. They are counted as open intervals, being that infinity is a concept of going on forever and not an actual location that you stop at. So if I were to draw this, which looks like an exponential function here, it means I'm starting at A, including A, and then as I go to the right on my x's, I'm just going to go on forever, which my B then technically would be that it's going to infinity. But since I can't reach infinity, or if I drew an open circle like this one, then I would put parentheses. So if I look at this first example, I have the function 1 over x. And if you've taken any of my classes before, especially pre-cal and cal, I really enforce you guys memorizing your parent functions. 1 over x to the first, which is raised to an odd number, is my elbows graph. So we know that this graph looks something like this. It's got the elbows in opposite corners. Okay. And we also have asymptotes going vertically and horizontally at each of the axes. Okay. Did not have any shift. This is just the parent function. Okay. So a few things we can say about this function. We can say, we obviously see that there's going to be an issue of continuity at 0. Now remember that continuity is read on the x's, which means left to right. So if I try and draw this left to right, I start here, I do my function, I have to pause at 0, and then I can continue drawing the rest. So far I know that there's a discontinuity at 0 because of an asymptote. So I can say x cannot be 0 because of an asymptote. It's one way I can say this. The next thing I can say is that there is a non-removable discontinuity at x equals 0. Remember that a removable discontinuity is a hole and a non-removable is an asymptote, okay? So the next thing we could say is that there's a non-removable all right, and then the next thing I can say is that the function is continuous, okay? If we look at the furthest left this goes, it goes all the way to negative infinity. Then it takes a pause at 0 because I do not touch it. It gets a parentheses, a union, and then it continues from 0 to infinity. Hopefully you saw a lot of that in your Algebra 2 and pre-cal classes. Okay, so those are some things I can say about this function based on its continuity. I can also say some facts about the limit at 0. Okay, so the limit as x approaches 0 from the right, as I come approaching 0 from the right, this limit of this function shoots upward to positive infinity. Now the limit as x approaches 0 from the left side, if I look as I approach 0 from the left, it starts shooting downward. And we had said in an earlier video that when the limit from the left and from the right do not agree with each other, we can say that the limit does not exist. And you could also see that here with your fingers. If I try and go to 0, they're going to different locations. So this next example that we have, we want to find out what's going on with this function. Now I don't know about you, but off the top of my head, I can't tell you what that graph looks like. But what I can tell you is that I am spotting in the numerator a squared minus a squared. And we talked about this last class, that that's called a conjugate binomial. So I can expand that numerator to say, okay, if this is x squared minus 1 squared, I can change that to x plus 1 times x minus 1. And now I can spot a removable discontinuity, okay? And this would reduce to x plus 1, okay? So I know what the graph of x plus 1 is. That's just a linear function that was moved up 1. Okay. With a slope of 1 to 1. And then I'm going to have a hole because this was removed. So this is going to give me a hole when x minus 1 equals 0. Which means my hole is at x equals 1. Okay. Now to find the y value of where that hole is, I plug it into the leftovers. So I plug that into my leftovers, and I find out that it is at 1, 2. Okay. So my hole is up here, my y-intercept is here, and you can see that nice rise over run is 1 over 1. And that's my function. So I can clearly see through the math and through the graph where the discontinuity is. It is at x equals 1. So there's a few things I can say. I can say that x cannot equal 1 because there's a hole. I can say that there is a removable discontinuity at x equals 1. And I can also say that the function is continuous everywhere except for 1. So I'd write that from negative infinity to 1. I cannot include 1 because there's a hole, so I'm going to put parentheses. And then from 1 on to infinity. Okay? I can also talk about the limit happening at 1. Okay? You can see that the limit from the right side and from the left side are approaching the same location. So the limit as x approaches 1 from the left and from the right, visually is very easy to see that it's going the same place. And I can see visually that I plotted the y value is going to be 2. If you had not graphed this, you would find that by plugging it, if you plug it in initially, you're going to get 0 over 0. But then when you clean it, you plug it into leftovers. So again, initially it'll give you 0 over 0. So then when I clean it, I'm plugging it into x plus 1, which gives me 2. Okay, so I talked about the continuity and I talked about the limit there as well. All right, for this upcoming question, we have a piecewise function, which in the previous videos we went over how to graph these. Okay. We said that these are simply just pieces of functions. So if I look at the top one, it is x plus 1, which is a linear function that has moved up 1. Right? So I would technically draw a line here, but it tells me only to draw it when x is less than 0 or equal to 0. So here's my 0 marker. Instead of drawing the whole thing, I'm just going to draw the portion that is less than 0, meaning the portion to the left of 0. Okay? And then x squared plus 1 is a parabola that was shifted up 1, but it only wants me to draw it to the right of 0, not including 0, but that's okay because it was already filled in by the other function. Okay? So, because the hole from the parabola was filled in by this function, and you're going to see that with our limits being kind of worked out even more so, there is no discontinuity because the hole gets filled in. So, this is nice because I could say a few things. I could say always continuous, or I could say continuous from negative infinity to infinity. Okay, so this is kind of verbally how we say it. This is mathematically how we write it. So now let's check out the limits. The limit as x approaches 0 from the right side would be us talking about the parabola. So if I plug 0 into the parabola, I have 0 squared plus 1, which gives me 1. The limit as x approaches 0 from the left, which is me plugging it into to the left of 0, the linear function would be 0 plus 1, also gives me 1. So we can see that the limit from the left and from the right agree. So I can say that the limit as x approaches 0 also equals 1, which again we can see visually because we drew our graph. All right, for this next function we have sine of x. And hopefully you remember your trig functions. Sine, I always tell my class, is like a stop sign. It goes over, then under. Okay. Now this, what we drew here, is just one cycle. These graphs continue doing that same wave forever and ever to the left and right. It's like a wavelength that continues forever. So the nice thing about sine, we can say that it is also always continuous. Or we can say with our math notation, continuous from negative infinity to positive infinity. Now this is something that is going to be true out of our 6 trig functions. Sine and cosine have the same behavior, that they have no discontinuities. They are continuous forever to the left and to the right. Our other 4 trig functions have an infinite amount of asymptotes, meaning tangent, cotangent, secant, and cosecant. If you don't remember what those graphs look like, feel free to look back at my videos of graphing trig functions. So unless it is sine or cosine, then we'll have our issue where we'll have to find our breaks. Okay? But for sine and cosine, we can say that the limit exists on all real numbers. All right, so looking at this next question, I have the 4th root of x minus 2. Again, if you've had me before, we've gone over graphs a lot. An even root shoots out on one side, and that minus 2 on the inside means that it moved 2 to the right. So we have a definite point right here that then shoots out. Okay? So radical functions are another kind of function, especially, only the ones with even roots that have an issue with discontinuity. So we talked about fraction functions 2 lessons ago. Radical functions are our other one, because although they seem continuous everywhere, so I've got a filled in hole, no gaps, I can draw it without lifting my pencil, this function only exists to the right of 2, and nothing exists over here to the left of 2. Okay? So for this function, we can say that it is continuous from 2, including 2, on to infinity. Okay? But we cannot say that this function exists to the left of 2. Okay? Some things we can say about the limit at 2. We can say that the limit as x approaches 2 from the left, okay, my function is y. From the left, there is no function shooting to the left of 2. Therefore, the limit as x approaches 2 from the left does not exist. When we analyze it, when we analyze 2 from the right, we see that the function comes down and on the y value ends up hitting 0. Okay, so we can say a true statement about the right side of this limit, but then the limit as x approaches 2, because from the other side, from the left side, there is nothing happening, would also be a does not exist. Okay? Now let's move on to this next question. I went ahead and drew this one for you. Okay? This is the function of a semicircle. Okay? And if you're in Cal, I'll probably take a moment and show this to you. If I put this as a y and I square both sides, I get rid of the radical, and then if I add this x squared over, you will clearly see the equation of a circle. When I do this on my own to get back to y by itself, I usually would apply a plus or minus in front of the radical, but because this does not have a plus or minus, it only counts the positive portion, which is why I only have the top part of this circle. The minus would have been the bottom half of this circle. Okay? So this function is only continuous between -2 and 2, and we include, you can see that they're filled in, including those 2 points. Okay? I'm not going to write every single limit scenario out here, but we can see that the limit as x approaches -2 will not exist because there's nothing existing on the left Okay, we could say that the limit as x approaches negative 2 from the right exists, and that hits 0 on the y. We can say the same thing about the limit as x approaches positive 2 the opposite direction, because it does have a function coming from the left hitting 0. It does not have a function on the right. Therefore, the limit as x approaches 2 does not exist, because it only has something from the left and not from the right. But the limit as x approaches, let's say 0, does exist, because from the left and from the right, they're going to the same location, which is 2. So I'm going to write a few of those down. We don't need all of them. Again, these are just hypotheticals that I'm giving you. We said at negative 2 it does not exist because it only exists from the right side. We can say the same exact thing about positive 2, that it does not exist because it only has something coming from the left. And then if I give one more random example, again, you wouldn't have to come up with these on your own. I would ask these of you. At 0, I am coming from the right and from the left. I'm going to the same place, which visually on the graph I could see is 2. But if not, you could plug in 0 here. It would cancel this portion out. You'd have the square root of 4, which also equals 2. All right, let's talk now about the continuity of a composite function. So if you could check each part of the function for continuity, and if each part is continuous, then the entire function is continuous, as long as the denominator does not equal 0. And then we also started talking, which we'll look at as well, how square roots work. Okay, and that'll be the last one we do. So for this first one, I have x plus sine of x. I know that x is a linear function that is always continuous. Okay, so that is good. And then sine of x, we talked already, is a wavelength that goes on forever, which also doesn't have an issue with discontinuity. So we can say that this function is always continuous. Okay, now let's look at 3 times tangent. We know that tangent has asymptotes at every pi over 2. That 3 we've learned in the past is just going to stretch the length vertically of this tangent graph. So this is going to be discontinuous at intervals of pi over 2. Okay, and again, if you don't remember your trig graphs, take a moment and look back at my videos of graphing trig functions. Okay, for our next one, our numerator is x squared plus 1. Okay, graphically that is a parabola like a U that shifted up 1. That means that one is always continuous, so my numerator is fine. Cosine is also fine because cosine, just like sine, goes on forever in both directions. The only issue I have here is checking when my denominator equals 0. So my denominator cannot equal 0. Now, if I think back to my unit circle, cosine is my x. My x is 0 when I'm at the top at pi over 2. So I'm going to be discontinuous when my denominator equals 0. So I could say when x is pi over 2, and at the very bottom, which is 3 pi over 2. Okay? Now for my next one, sine goes on forever, has no issues with discontinuity. Let's underline our answers here. The 3 being multiplied to the x is just going to stretch this horizontally. So stretching it won't affect my continuity, so this one is always continuous. This one's good. Okay? And for my last one, I have square root of x squared plus 1. Remember, even roots have an issue that we have to take a look at. And a quick recap from Algebra 2, the way we check discontinuities with even roots is we set the inside greater than or equal to 0. So x squared plus 1 has to be greater than or equal to 0. That should also make sense to you, because if I get something less than 0, that means I get a negative inside of a root, which gives me an imaginary number. Okay? So if I start moving things around, x squared has to be greater than or equal to 1. Now, I know that this is always going to happen because if I square anything, it's always going to give me a positive. Okay, and even if I look back to here, if I square something and then add something to it, I will always get a positive number. Anytime I square it, I won't get a negative. If this was a -1, then I would have had an issue. Okay, so here I could also continue and do square root to both sides. And I could say x has to be greater than or equal to square root of 1, which is 1. So I'm good. Okay? Sorry, I made a little error here. This should be a -1. And if I square root a -1, I get an imaginary number. Okay? So the fact that x has to be greater than an imaginary number, and my functions, my graphs, only have real numbers, lets me know that that will always happen. Okay? If this arithmetic to it throws you off a little bit, guys, just think of any number. Could I plug in a number here that will give me a negative in a square root? And the fact that I have a squared and then I'm adding means that I'm always going to get a positive. So this is always continuous. Okay? Now, if any of these felt confusing for you, I want you to pause the video, go to desmos.com and click on the graphing calculator and plug each of these in, and you're going to get a nice visual of each of these graphs, and you're going to see how this matches out. All right, I'm going to take a moment and break down this tangent graph for you a little bit more. So we should remember that tangent looks a lot like an x cubed graph. Okay, but they have asymptotes at pi over 2 and negative pi over 2. Okay. Now, remember, this is just one cycle. This function, if I were to keep going, okay, would continue on again. And if this is a cycle of an entire pi, from negative pi over 2 to pi over 2, that's one full pi. That means I'd add a whole pi to pi over 2, which would give me 3 pi over 2, which you could see is another multiple of a pi over 2. Okay, just to show you two cycles really quick. So when I talk about the continuity, I could say that this is discontinuous at intervals of x equaling pi over 2. Okay? I could also say that tangent is continuous within its domain. Because if the domain of a tangent function is just each of these, within each of these, they are fine. It's just where the asymptotes happen. Okay? So now, if I want to talk about a limit, let's talk about two different limits. The limit as x approaches 0 of tangent. So as I approach 0 from the right and from the left, I hit the origin, which is 0. So that one's fine. But if I talk about the limit as x approaches pi over 2, okay, I can see that from the left limit of pi over 2, I shoot up to positive infinity, and the left limit shoots down to negative infinity. Okay, so for that reason, because from the left and from the right, they shoot in opposite directions, or the fact that they don't even go to the same location, we could say this does not exist. All right, the last thing for today is one of the 6 very important theorems that you'll learn in calculus. If you have me, I'll have you memorize them. They come up a lot in the AP test, okay? And this, luckily, is one of the simple ones. Wording-wise, it sounds a little tricky. So I drew you some visuals to help you understand this, okay? This first arrow goes with this visual. It says, if f, the function, is continuous on the closed interval from a to b. So meaning counting a and b, this is continuous. And f of a, meaning the y value at a, is not the same as the y value of b. You can see they have different y values. and k is a number between f of a and f of b, meaning it's a y value in between those two, then I can say that there's at least one number c in a and b, meaning a number in between the a and b, the x's, where f of c is equal to k. Long story short, guys, if this x value gives me a higher y or a lower, vice versa, that they're different y's, then I know for a fact that there's going to be a point that exists in between those x's and in between those y's that correlate with each other. When you play this out in a drawing, this is like a very duh theorem. The reason why calculus likes to use this theorem a lot is because IVT, intermediate value theorem, can be used to prove and locate zeros, which zeros do become very important later on in calculus. So for example, if I can prove that that f of a is a positive number and f of b is a negative number, that means that somewhere in between, and of course assuming it's continuous, I had to have hit the x-axis, which means that I have a 0. Now, if for whatever reason the IVT test, when you're working it, fails, it doesn't mean that there is no point in between that exists. It just means that I do not have enough information. So this is not a test that I can use to disprove things, only to prove, because if the test does not work, it just means not enough info. So let's look at this last question for today. Use IVT to show that f of x, which is an x cubed function, has a 0 between 0 and 1. So the first nice thing about this is that I know that this function is a cubed, means that it looks something like this if I know my graphs, with some sort of shifts, which means that this is continuous. Okay, there's no holes or asymptotes in that polynomial. So according to my theorem, I want to be able to find if I have a and b. The fact that it says in between lets me know that this is not an ordered pair. This is my first x and my second x, like my a and my b, is going to be to find f of a and f of b, what those two y values are. Okay, so let's start off by saying f of 0 is going to be 0 cubed plus 2 times 0 minus 1, which this gives me negative 1. And then I have f of 1, which is 1 cubed plus 2 times 1 minus 1, and this gives me a positive 2. Okay, so back to this image we had drawn. The fact that one of my y values came out positive and one came out negative, and I know that this is going to be continuous. These are your y values. Imagine drawing from negative 1 to positive 2 on your graph. You will indeed hit a 0. So you can say by IVT, f has a 0 between 0 and 1. Okay? And if you want a quick visual, just so you can have an idea, what we just discovered is that you had 0 comma negative 1. Okay? And then you had 1 comma 2. So if I'm going to draw a continuous function, okay, between these 2 points, whether it swivels or not, as long as you don't lift your pen, I know I definitely had at least one time that I had to cross through the x-axis, which gives me a 0 in between those two. Okay?